Hello, Gordon.
Hello.
Hey. Hey, Christian.
Sure.
Okay. You have homework 6. Friday. And if you submit this early, I'll try to grade this, especially if you really want me to grade it, just send me a one-line email and I'll grade it right away for you guys within a few hours. There's a midterm 2 on Friday, as we said. The midterm will cover homeworks 4, 5, 6, and 7. It means all the topics related to that. Especially, I noticed that some of what I thought was expected to be simple, many of you guys got it wrong. So if I've taken off too many points, that's an indication that it is expected that you guys know the topic, and I might ask that in the exam. But you'll have more time to do the exam. So this is the exam is going to be online. Online means the exam will be available online. So this will be uploaded by 2 p.m. Friday. Could even be before. And the submission due date, submit by midnight. So that's going to be the okay. Any questions on that? Okay. We were doing Lorentz transformations, and we want to talk about what are the implications of Lorentz transformation. So let's call this implications of Of course, the most popular ones are length contraction and time dilation, which you probably have heard about in other courses. I will talk about that, but I want to talk about a few more things. So what is Lorentz transformation to begin with? If you have, let's stick to one dimension. So there is space being measured along in the horizontal direction, that's z, and you measure time. So that's the two quantities. The two quantities we are talking about. So z and c times t. Of course, there is x and y also, but we keep that fixed so that everything is happening in one dimension. So we're measuring time and position. And we pointed out that if there was another observer which is moving with respect to the first observer who measured the z and t, then things get transformed. Then the second observer will actually measure c prime and ct prime. C is just a scale, you can set c to 1 if you want. So if there is one observer measures position and time, second one, if it is relatively moving with the other observer who measured it, they are different. And gamma here, so beta first of all is v over c, a dimensionless quantity which is always less than or equal to 1, and gamma, which is equal to 1 over 1 minus beta square, is always greater than or equal to 1. Okay, so that's your quantity. So let's begin by saying, or let's have an analogy here that similarly, if so, this is to deal with space and time. So there is another transformation which is a lot more intuitive for us, and that is rotation. And let's think of rotation. So this is x prime, y prime. And if you were to rotate your axis by in a certain amount angle theta, so sine theta, and minus sine theta, and cosine theta, that's x and y. That's very intuitive there. What is happening when we are talking about rotation is you have a coordinate system, so there is x and y. This x and y is not necessarily related to that because this is a different independent transformation. So it's not that whenever we are moving z and zt, the other two coordinates are getting rotated. That's completely independent. Okay, so how can we find the x prime, y prime with respect to xy? There is one way of seeing this is the following. Draw a circle. So this is a diagrammatic picture if you want. So there is a point x comma y here. And the question we are asking is, if I were to change my coordinates, that means to say I rotated my axis here like this, then with respect to my new axis, x prime and y prime, this has moved, right? This is now closer to the x-axis. Here, this was almost making 45 degrees with respect to the x-axis. In the new coordinate axis, x prime and y prime, it is making it slightly smaller. If I were to go to another coordinate system, x prime double prime, then it will be almost on the x-axis. That's called a passive rotation. That means to say that the point itself is not rotating, it is the axis that is rotating. Right? That's one way of viewing this, but there is another way of looking at this, that keep everything straight and let the point move around. That's called active rotation. So let's say another way of looking at this is So this is your x and y, and that's your x prime, x comma y, and x prime y prime. If I were to rotate, this will move. So this could be the new. So in this case, this gets closer, right? So this could be your x prime y prime. So if I rotate my axis by a certain amount, this coordinate moves this way. If I rotate it by some other angle, that's x double prime, y double prime. These are all different observers associated with each of these rotations. I can make another one somewhere here. That's triple, right? Notice it's the same point we are talking about. It's just after you rotate the frame, this point goes there. So which means to say that every point on that circle, in principle, will be seen by someone. If you rotate your axis sufficiently, that point will move around that. So that's the key feature there. And circle plays an important role in this rotation, right? So this is rotations. And circle is an important concept there. So each observer can be associated with a point on the circle. Think of all possible rotations in 2 dimensions, and each of those rotations will take this point to somewhere on that circle. That's one interpretation. What is the analogous understanding of Lorentz transformation? So let's see. We already noticed that if I were to calculate minus c squared t prime squared plus z prime squared. That comes out of the, if I were to substitute this, minus of c prime t prime is beta gamma times z, like a matrix equation, plus gamma times ct. I'm just reading it off from here. Ct prime is beta gamma times c, gamma times ct, like as if I'm multiplying a matrix. And plus z prime square is gamma times z plus beta gamma times ct square, which is equal to collect this all together. So I have minus of so let's see. So this is minus beta square gamma square and gamma square. So that's z square comes with gamma square is there, and then there is 1 minus beta square. And what about ct square minus c square t square comes again with gamma square times 1 minus beta square. And there are cross terms which exactly cancel out, because there is the same cross term with this and with that, so they cancel out. But there is one more feature, that gamma square times 1 minus beta square, by definition, if I were to do, so this implies that gamma square is equal to 1 minus beta square. So that means gamma square times 1 minus beta square is equal to 1. So that leads to the idea that this is z square, or if I were to write this first, minus c square t square plus z square. So what is the equation of a circle? Remember here, if I were to think of a circle, you're having x square plus y square is equal to x prime square plus y prime square. And that remains a constant. So let's say r squared. So if this is a constant, you have a circle. Here in Lorentz transformation, it seems like we have z square minus c square. T square remains a constant. Right. What is that curve? That's not a circle. And if you look it up, or if you're familiar with it, that's a hyperbola. So what does that mean? So we have, let's draw z and t this time, and it is just conventional practice that you write z on the x-axis. The position is plotted on the x-axis, and our time is plotted on the y-axis. And this time we have c times t there. Clearly, it seems like if this is a constant and because there is a negative sign, notice again, go back to your circle equation. If you add two squared quantities, that radius will always be positive. That's no more necessary here. Z square minus ct square. I can always think of a position, for example, z could be the origin, right? Then as time evolves, this becomes negative. So this could be negative, it could be positive if I choose z to be very far at time t equal to 0. That's positive also. So there are three possibilities. It could be 0, positive, or negative. Right? So this constant could be negative. It could be 0, or it could be positive. That's one realization, and based on that, you can actually get this equation of the curve would be the following. First of all, there is a special line which makes a 45-degree angle. We will see what's the significance of that. And this constant curve is the following. Like there are 4 of them. It's this. And that's here. These are hyperbolas. On each of this curve, your quantity z square minus c square t square remains invariant. Okay, remains invariant means remains the same. Now, what does that mean? Let me first, let's say that the z, one of them is, so that there's a vector here. So this is at origin, and that's your coordinate, right? So that's z comma ct. So if you want this point here is z comma ct. Now, like we did in rotations, what we said is that if I make a rotation transformation, since I have to keep x square plus y square constant, it will move somewhere on that circle. Similarly here, this is one observer. If there is another observer moving with a velocity v, the only thing it can do is that it has to move around on this curve. So depends on where that observer is, what's the velocity with respect to this observer. It could be somewhere here. So that could be your z prime, ct prime. So let me write that as z prime, ct prime. Right? So this is the Lorentz transformation of z and ct with some velocity, positive or negative. Again, make another Lorentz transformation. This could become z double prime and ct double prime, and so on. But it has to be on this line, on this curve, on this hyperbola. Not any of these 4 ones. It has to be the one in the particular cone that you have. We say cone because this is a 3-dimensional, right? In general, this is not just 1 dimension here. There is 3 dimensions here, so you can rotate. Think of rotating this, and that is called a cone. So this will be called a time cone. This will be called a position cone. And we'll come to that. And so whenever you make a Lorentz transformation, you're on that line. If you begin with positive, so if your coordinate you're talking about is in this vertical top cone, then necessarily, because these are 45-degree lines, the z has to be less than time, right? Position has to be less than time because as you can see, the x component is smaller than the y component. So everywhere on this cone on the top, z is less. If z is less, that means it is negative. So whenever it is negative, this is called a time-like vector. So that's a definition. That's because if it is negative, that means time dominates. So it is time-like vector. On the bottom also it is negative. So there is a positive and a negative quantity. Both will be the same constant. So that will come out, but it can be on either side. But once you have a coordinate on one end, it can only move around. By Lorentz transformation, you can only go along that. You have to stick to that cone. If it is 0, where is this? That's on that 45-degree axis. And in that case, actually it is 0. That means z is exactly equal to c times t. And that's the equation of a light traveling. Right? Light actually travels with that equation. Distance traveled is exactly equal to c times time. So this is called light-like whenever it is 0. So that's a very special, it's a surface of the cone. It's light-like vector. And if it is positive, it is a space-like. And all these are possible. And we will say that there are some features associated with each of this vector. So now that we are talking about this z square minus ct square, we should talk about two things. What is the distance? So whenever we think of a space, there is at least two important characteristics. One is distance. And second is what do we mean by orthogonality, right? Whenever we think of the geometry of a space, we have to imagine what is orthogonality. So that's orthogonality. That means to say that if I give you one vector, give me the vector that is perpendicular to that. And in rotations, you will have no difficulty if I tell you that that's a vector. Find a vector that is perpendicular to that. You will immediately intuitively say that, oh, that's my vector that is perpendicular to that. It could also be along this direction, so that anything on that plane is perpendicular. But now if I were to ask you, oh, what do I, if this is a vector, what do I mean by perpendicularity there? So that we will be able to go back and ask, what do we mean by perpendicular? What do we mean by distance? First of all, the distance between two vectors here is x squared plus y squared, right? x1 minus x2. So here it is x1 minus x2. Here it is distance is equal to z1. So if there are two coordinates, z1 minus z2 squared minus, not positive, it is minus c squared times t1 minus t2 squared. So distance is very skewed in the sense that there is a negative sign in there, and that takes away all the intuition is completely gone. Right? When we think about what's the shortest distance between 2 points in a Euclidean space, and we have an intuition for that, but that doesn't work for the space that we are talking about, and this is often called Minkowski space. Minkowski space and time, if you want. So, okay, so distance, how does this actually come in? And that's actually where the orthogonality shows up, and orthogonality is very closely related to what is called a scalar product, which actually tells you the both quantities, distance and orthogonality in there. So let me talk about rotations here in a minute. So you first talk about a scalar product between vectors, right? A dotted with B. If I have two vectors, A and B, A dotted with B is defined as AX, BX, right? Plus AY, by. So that's what is needed to define my dot product. And then there are two things I can do. If I choose A and B to be the same, that defines my distance. Right? If I choose this, for example, to be x and this to be my same vector A is also x, so this becomes x squared and that becomes y squared. So once I have a scalar product, so this is called the scalar product. And then if I choose A to be exactly the same as B itself, that gives me the distance. And if I choose it to be different, and if I set if so if A is equal to B, that gives me distance. So A dotted with B is equal to vector A squared, and that gives me the distance. And that's always greater than 0, and that's remains constant, right? Length of a vector remains the same under rotations. And orthogonality is, if I were to have, if I ask the question for what B, for a given A, for what B is this equal to 0? And then you would say, oh, I have to look for quantities where AX, BX, plus AY, BY is equal to 0. And you would say there are a bunch of them. So as far as the ratio of the components is exactly equal to minus of AY of AX, then they're orthogonal. Right? That's an algebraic way of saying it, but we know what orthogonality is in rotations. But here, similarly, what is the scalar product in Lorentz transformation? So, write that down. So if I have a vector 1, so I have Z, so let's say a scalar product in Lorentz transformation. And it is, if I have two vectors, Z, comma, CT, and there is another vector which is Z prime, comma, CT prime, my dot product will be, so let's say scalar product. We will have a notation for this very soon. This is equal to Z times Z prime minus of C times T times C times T prime. So distance is when you set Z equal to Z prime, that's equal to Z squared minus C squared T squared. And already we see a problem here. Oh, distance. The way we intuitively think of distance is always greater than 0, like length of an object. That's because we think of distance in rotations, right? That's remains the same, and you give a fundamental meaning to that. Here, it doesn't have to be positive. It can be different, but it has to remain the same under Lorentz transformation. That's the only requirement. And what we are interested in, orthogonality. When is this orthogonal? And we see that this has to be equal to 0. That means Z over CT, the ratio, has to be flipped. Right? So this is CT prime over Z prime. Right? So if you flip the coordinates, that gives you the orthogonal vector, at least one orthogonal vector. So let's see what are the orthogonal vectors immediately. So that's your Z and CT. So what's an orthogonal vector in this space? Remember again your 45-degree lines which represent the line along which a light will travel. And let's have an arbitrary vector here. So that could be your Z comma CT. That's a vector representing the coordinates z and ct. What is perpendicular to this? The idea is to flip it. So flip your coordinates ct and z as a numerical quantity. If this is 3, 1 or 1, 3, then you want to make it 3, 1, and you will immediately see that the vector is here. So in the angle, in the real sense of the angle in three-dimensional or the Euclidean space, make the same angle on this side, and that will be your perpendicular vector. Always, there is a theorem that a time-like vector will have an orthogonal vector which is space-like. And this will have some consequence later when we are discussing velocity and acceleration of a particle. So this is orthogonal. So this is orthogonal. So that leads to an interesting feature, and this is only when it is time-like. So this is a quiz. I'll let you guys figure this out. Quiz: what is orthogonal to a light-like vector? Orthogonal vector for a light-like vector. So if you have a time-like vector, its orthogonality is given by space-like in this manner. If it is space-like, do the opposite. Inverse of that is your time-like. But then somewhere in between is like-like. You would say that, oh, it's a like-like in itself the case. But then check if that is the case. You should be able to show that that's actually equal to 0, and I'll let you guys check on that. So that's some intuition about perpendicularity and distances in Lorentz transformation. Any questions at this stage? Comments or questions? Okay, so next interesting feature that comes out is that, or before that, let me think of, let me talk about what is a world line. World line of a particle. So let's again have the space-time diagram. That's space-time, and that's your z, and that's your ct. And remember, first of all, if you have an origin, so that's, let's say from here, if you were to emit light, light will go, so light is born here. Let's say there is a bulb, so light gets produced here, and it has to go at 45 degrees, right? Z has to be equal to ct, so light will travel along 45 degrees. And this will go in this direction also. That's the only two directions it can go as far as z and t is concerned. Of course, x and y is also there, so it will come out of the board also. But this is at that instant, right? At t equal, so whatever light was produced at t equal to 0, at t equal to 1 second, it is somewhere here. At t equal to 2 seconds, that's here. 3 seconds, it's here. So that's if you want the world line of light. So this is the world line of light. If that particle was going, so it will move away from the origin and move out, right? At t equal to 1, it is somewhere here. T equal to 2, it is somewhere here, and so on. So it's actually moving out. If it decided to go to the left, it is on the z-axis. It will move to the. All right. So that's one thing. But now let us say that you have a particle at z equal to 1. So that's a constant value for z, and it is just sitting there. Right? You can always think of a particle like it could be one of us. We are just sitting on our chair in our house, and for a long time, you just keep sitting at in that chair, and your path will be, what is your whirl line? You're basically having at z. Z remains fixed, right, for all time. So you will just go straight. So that's a whirl line of, so this is at rest. And by rest, I mean it is at rest with respect to this frame. So now rest is no more an absolute quantity. It changes from one person to the other. What if you're moving? So there is another person here who is a neighbor of yours. And so this could be your house, so house number 1, that's house number 2, and there could be a grocery store somewhere here. Right? There's a grocery store here, and your neighbor decides to go from the house to the grocery store, and the person will move with a speed that is slower than speed of light. And that would mean that it cannot go beyond 40. So if you go with speed of light, you're going at 45 degrees. So if you go beyond that, you're going faster. Right? You're covering more distance than light can cover. So it has to be smaller than that. So this could be significantly faster, let's say. So that's your moving particle. Now, while this person is moving, if you were to want to communicate with this person, so you have, that's your H1 sitting at home, and that's a vertical line, and that's a person moving away from your house and going to the grocery store. But let us say that you decided to call this person. You will use a cell phone, and cell phone uses light waves, right? Waves that are moving at the speed of light to communicate with that. So how does that communicate? So at t equal to 0, let us say this is...
Move the camera down, please.
Oh. So it's the same H1 and H2 I was talking about. So that's H1, that's H2, and let's say that somewhere here is the grocery store. Right? And while your friend or neighbor is in the car, you decide to communicate with your neighbor, and you use your cell phone, which means you're using light to communicate. And what is happening is that has to travel with at 45 degrees, because that's light, right? So it will go and intersect. So that's if, so it gets emitted at some time, and it reaches your friend at another time here. And your friend communicates something to you, it has to come back to you at 45 degrees, right? So this is 45 degrees. So again, travel at 45 degrees, and whenever it intersects, that's when you get back that signal. Since H2 is going so slow typically in real life, this almost happens instantaneously. That happens very quickly. It hardly takes any time, and you hear back very immediately. But if you were to send a signal to Mars, how much time does it take to send a signal to Mars and come back, by the way? Like if you were to have a friend in Mars in the future, how much time do you think you say hello, and how much time will it take for it to reach, the hello word to reach there?
I would say a couple minutes, right? It has to be less than 8 minutes, right? It's closer to us than the sun is.
That's correct, but it depends on whether Mars is on the other side of the orbit or on this side of the orbit. Yeah, you're correct. So it's around 8 minutes. So if it is closer, it could be 6 minutes. But if it's on the other side, it could be 12 minutes. So recently when they sent the rover out there, it was taking about 12 minutes. I think what happens is that they shoot it when it is close to us, but by the time it reaches there, it takes about 6 months to reach there, right? So Mars has gone on the other side of Sun. Either Mars has gone or we have gone on the other side. So it takes a long time to have signals communicating at this, and that gives you a picture of what these world lines represent. But interesting feature here is that if I were to have a world line, let's say here, and so this could be your, so as far as, so how do I know that? So I could say that's a world line, and I can ask you, oh, is this a world line at all? Is this possible or not? Is it ever going faster than speed of light? And you would say at each point you will come and check, is it more than 45 degrees or not? And the way to check it is that at each point you put a cone there. You put a cone there and you should make sure that the world line is inside of that. So this seems like it is not an appropriate world line, so it should be within 45 degrees. So you would say anything like this is the world line. And then you can see that wherever you draw your cone, this should be within that. Oops. So it should enter from the bottom part of the cone, and it should, that's you. So it should enter from the bottom cone and get out from the upper cone. That's the signature of an appropriate world line. Otherwise, it's not an appropriate world line. Okay, so that's your world line of a particle. And then we have the first non-trivial feature now is, so let's talk about a non-trivial feature like length contraction and all, and this is to do with simultaneity. So let's again have, we're using a lot of diagrams to show this, but this can be algebraically done also, but algebraically there's less insight. Okay, so let's have a space-time. Let me choose one of the cones on the right. That's your Z, and that's your CT. Now, you could be having, you might be sitting on the origin, at the origin, let us say, and your neighbor is a certain distance away on the Z-axis, correct? And your neighbor is also at rest in the house. And let us say you do something in this frame. Whenever this incident happens, you ask, what's the time difference between the 2 points, right? The 2 points that I've written is at a specific time, and that's at t equal to 0. Right? So these 2 points, this happens at 0 time, t equal to 0, and this is also t equal to 0. So you would say that's simultaneous, right? So that could be 2 babies born in 2 houses. Right, and they were born simultaneously according to this frame, right? According to the Z and T frame, that's simultaneous. But now let's do the following. So remember, if every point on this curve, the hyperbola, is actually a transformed version of this coordinate. So let's say your neighbor is at this point according to this frame, but if for someone who is moving with respect to this frame, your neighbor is somewhere here. So this is in the future. Why is it in the future? Because the time for this is in the future. This type is in the future relative to the origins. If I were to go to another frame, any point on this hyperbola corresponds to an observer seeing this event. So there is another point, let us say here. So that's in the past. That's because, but that is assuming that these, and this could be 3 different events in this frame, but in our interpretation, we said every point on this curve is equivalent to an observer seeing this same event in a different manner. So different observer conclude differently. Your Z, the coordinate that I have drawn, that's particular observer says this is simultaneous. Another observer says your neighbor, whatever happened with your neighbor, that was in the future. And another third observer says that it is in the past. So simultaneity is relative. A simultaneous quantity, or just the idea of simultaneous, is relative. So we should never talk about simultaneity. So if you do an experiment and you say that, oh, I made sure that this and this happened at exactly same time, if someone else were to do the measurement, they will disagree completely. For that matter, any measurement of time and position will disagree. So what's the right way? So simultaneity is relative for that matter. So let's go back to rotations again for analogy. Rotations. So what happens in rotations again? So that's your X and Y. That's your circle along which things go. That's your X and Y. So if I were to give you an event which has an X component of X and Y component of Y, and let us say you measure X, right? And there is another frame which measures it to be X prime, Y prime. And now you come back, so this is one observer, so observer 1, so observer 2, let's say. So that's observer 1. And if there were 2 observers, they do an experiment of measuring the X component X, and another person measures X prime, and they come together and say that, oh, I measured my X component to be X, and the other one says that I measured my X component to be X prime, and they won't agree, right? Right? If it is a rotated frame, they won't agree. But that's not surprising because we never compare components. Right? This is not equal. That's equivalent to saying you measure the shadow of a quantity, right? So this is a shadow. Like instead of measuring the height of a person, if you were to measure the shadow of a person, it depends on where the sun is, right? You will never measure the height using a shadow. That's not a correct experiment at all. You're asking the wrong question, right? So you never measure components. Same thing now. Now here in Lorentz transformation, what it is? Lorentz transformation, what is invariant is Z squared minus CT squared is a constant. Look for the constant, not Z, not time. If you measure position, oops, it's not on the screen. Oh, was I showing the right way? Probably it was not visible, right? Okay, sorry about that. Yeah. When we are talking about the Lorentz vector, similarly, you never compare positions. Z will not be equal to Z prime. T will not be equal to T prime. Two different observers will measure different times. That shouldn't be surprising. Like exactly like shadows do not match. But what do you measure? You measure the length that is invariant. So you should always measure x square plus y square, right? That's our length of an object, right? That's your length, L. That remains the same between rotation transformation. Here, similarly, this constant is the important one, and we will call that constant minus s squared is equal to minus c squared t squared plus z squared. And s here will be called the invariant distance. So the key point in Lorentz transformation is that don't associate any meaning or never compare measurements. It's not the same meaning, right? Time is time, what we know, but never compare your time with another observer's time. That's not a good question to ask. It is the invariant distance that is more important. And then comes the question, so our theme would be, so how do we proceed now? So this is going to be our goal here. Remember your kinematics, how do you do physics? Go to your introductory physics. What you do is, there are a few things. First, you define time, right? First thing you do is that you, I wouldn't say define time. You say that, oh, there exists time, something that is monotonic. It keeps increasing, never comes back, right? It always grows. So that's time. And then there is position. Right? Let's call that z. Right? So that's given. Once you know these two quantities, you define velocity. Velocity is defined as dz over dt. And then you define acceleration, which is dv by dt. So you do calculus there, right? So first you say there is a notion of time and space. You define velocity and acceleration. And then again, there is magic. We don't know what is mass. We don't know what is force. We don't define that. We have an intuitive feel of what mass is. We have an intuitive feel for what forces. And then we write Newton's laws, right? We say, oh, F is equal to mass times acceleration. And so this acceleration is associated with motion. And we say, Newton tells us that this is always true. We want to do exactly the same thing, but we are now stuck here because time and position are relative quantities. And even the ratio dz over dt is relative. Velocity comes out to be relative. So we want to define something which we can compare with. There's nothing wrong in velocity, but we want to come up with a new quantity like invariant distance, which I can measure and then ask someone else to measure it, and they will measure exactly the same thing. And that's what we are going to talk about. So we are going to talk about invariant quantities, something that does not change between observers. For every physical quantity, like velocity, we will talk about an invariant velocity. Acceleration, we will talk about an invariant acceleration, invariant force, invariant energy, invariant momentum, and so on. Right? And it will be relatively straightforward, and it will all be built out of this invariant distance. Right? That's what we will do. So first, we will have the exam on Friday, and then on Monday, we'll quickly get into the kinematics of relativity. That's all. Thank you. Mm-hmm.
Do we still have lecture on Friday?
No, let me not have it. I think I don't mind because I'm behind in the course, but let me not keep it at this moment. I might, yeah, maybe a question is, do you guys have a class after this, right after this?
On Friday, I have a meeting after this, but
But Monday and Wednesday you don't have?
Monday and Wednesday, I'm good.
Yeah, so maybe I should ask this to other students, if by any chance, if all of you guys are free, then what I've noticed is that I did a similar thing in graduate classes, in my graduate classes, and it was not my idea. Students suggested that, oh, you take extra 10 minutes every lecture. And that has been really beneficial, because most of the time what happens is that I'm in between some thought process and I might have only 10 minutes to finish. But when I bring it back in the next class, I have to summarize the whole thing. It takes 20 minutes to do that. So just having 10 minutes extra every lecture, or even if it is two times in a week, I've noticed significantly speeds it up. So we can check if others are available, and that might really help. But otherwise, we will see how far we can go.
Okay, that'll work.
Sure.
Fine with me.
Yeah. Was it okay? Was this useful? Have you guys seen this all before?
Kind of a little bit just from
Yeah, a little bit.
I guess potpourri seminars and a little like surface level, but I thought it was really interesting. I actually really enjoyed the lecture today.
Okay, good. Yeah. But ask me, I mean, most of this, because it is geometric, sometimes you miss out. But feel free to ask questions or interrupt me and all that. Yeah. Okay, so even you have any questions right now? Yeah. Okay, good. Yeah. Okay.
Thanks.
All right.
Yeah, enjoy, guys.
Take care.
Yeah. Bye, Borden. Bye, Christian.